tutoring. In this video, we're going to be looking at magnetism, magnetic forces and fields, and this is video number 1 of 3 for our magnetism and electromagnetism topic. So let's crack on. Electromagnetic effects are used in a wide variety of devices. Engineers make use of the fact that a magnet moving in a coil can produce electric current, and also that when current flows around a magnet it can produce movement. This means that systems that involve control or communications can take full advantage of this. The poles of a magnet are the part of the magnet where the magnetic force is strongest. If you are looking at a bar magnet, as you can see here, the poles are found at each end. There is a north pole, which is marked N here, and a south pole, which is marked S here. When two magnets are brought close together, they exert a force on each other. Most people know that magnets will either repel each other or attract each other, but what decides whether a magnet repels or attracts? If poles which are different to each other are brought together, they will attract one another. For example, a south pole and a north pole will have attraction. If poles which are the same as each other are brought together, they will repel each other. For example, a north and a north pole. In our forces topic, we split up forces into two categories: contact forces and non-contact forces. So what type of force do you think magnetic force is? Well, it's a non-contact force, as the magnets do not need to be touching in order for the force to exist. A permanent magnet produces its own magnetic field. A permanent magnet is the one which retains its magnetic properties regardless of where it is placed. Permanent magnets produce their own magnetic field. Magnetic field lines show the direction of magnetic force at that point in space. A permanent magnet will create a field, and the field strength will be most at the poles. Here is what the magnetic field looks like around a bar magnet. An induced magnet is a material which becomes a magnet when placed within a magnetic field. Induced magnetism always causes a force of attraction. But when you remove this magnetic material away from a magnetic field, an induced magnet loses most or all of its magnetism quickly. This is very important, so we will go through this again. An induced magnet is a material which becomes a magnet when placed within a magnetic field. Induced magnetism always causes a force of attraction. When removed from the magnetic field, an induced magnet loses most or all of its magnetism quickly. So there is a difference between a permanent and induced magnets. Permanent magnets will produce a magnetic field wherever the permanent magnet is. Induced magnets will only become magnetic if placed within a magnetic field. Permanent magnets will have a consistent north and south pole, whereas induced magnets will polarize themselves to always be attracted to the permanent magnet in a magnetic field. Now, there are 4 types of material which can become magnetic when placed in a magnetic field, and you need to know what these 4 materials are. And when I say these 4 materials become magnetic, I mean that these could be induced magnets. Iron is the first example of one of these materials. Steel is as well, as is cobalt, and so is nickel. So if you take any of these materials and place them within a magnetic field, then they will become induced magnets. The region around a magnet is called a magnetic field. Magnetic field lines point in the direction of the force which a north pole would experience at that point. Magnetic field lines point away from north poles and towards south poles, and that makes sense. If you placed a north pole near a north pole, you would expect it to move away. The density of magnetic field lines determines the strength of the magnetic field at that point. More field lines in an equal area means more magnetic field strength. The strength of a magnetic field depends on how far away you are from a magnet. The closer you are to a magnet, the stronger the field. And remember, an induced magnet will always be attracted to a permanent magnet when it's placed in a field. So if you take this circle that I've drawn here and look at the field lines, you'll see that they're very close to each other. And when you've got lots of field lines close to each other, it means you've got quite a large magnetic field. So if you placed a North Pole here, it would experience quite a large force. Here, there's fewer magnetic field lines in the same area, so that means there's less of a field strength there. In here, there are no field lines at all. There will still be a field, but a relatively low field. The further away you get from a magnet, the lower the field strength. Now, the Earth actually has its own magnetic field. In fact, it is this which allows a compass to point in the direction of north. A compass is actually a tiny bar magnet which is allowed to rotate and point in the correct direction. Because of the Earth's magnetic field, there is a magnetic force which acts upon this small magnet and orientates it in the correct direction. And you can actually plot a magnetic field of a bar magnet using a compass. So we can use a compass to plot a magnetic field around a bar magnet. In order to do this, we must start with the magnet itself, some paper, a pen and a compass. Firstly, we'll place the bar magnet on the paper. And secondly, we are going to place our compass near the pole of our magnet. So I've drawn this out here. If you get some paper, you put your bar magnet on and you place your compass so it's very close to the South Pole. Next, we put a small cross on the paper at the south end of the compass. Now we place the north end at this cross and repeat the process. So we'll put the cross there, and then we'll put our North Pole at the cross. And then we'll just carry this on until we have crosses all the way around in a circle like this. Now we connect up our crosses and draw in an arrow. Remember, magnetic fields always go from north to south. So the key points to remember from that: when drawing a magnetic field pattern around a bar magnet, there should be lots of lines close together near the poles. This is where the field is strongest. Remember, the direction will change depending on where you are around the magnet. When you are near the magnet's south pole, the field will point towards the pole, and when you're near the north pole, the field will point away from the magnet. Because a compass works on the surface of the Earth, it means there must be a magnetic field present on Earth. The core of the Earth is actually magnetic itself, and that's because it's made of a magnetic material, and that's iron. This is what causes the magnetic field on Earth. If you're following along in your revision workbook, pause the video now and complete task number 1. Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backrowtutoring.com.